deals with the logic of and with respect to simple matter. So it's actually the very actually the theoretical um, part for the computer system, modern computer system. Uh, so basically, automata enables the scientists to understand how machines compute the functions and solve problems. So this is actually, so if we try to understand how this machine works, like in modern days, we talk about AI, artificial intelligence, and in order to understand this, we need to understand how machines computed functions and solve problems. Okay. Now, here's some of the terminologies related to the finite automata. Um, so in this finite automata, in a we we're going to introduce a couple of terms that are used in the finite automata. The first one is a symbol. So just remember these terms. Um, so symbol is basically the smallest building block, which can be it could be anything, like an alphabet, like English characters, and or pictures, or some kind of icons. So any actually small object or alphabet, digital numbers, um, you can think think of any of these as symbols. Okay. So basically, once you're given a symbol, you should be able to tell the difference between two symbols. Okay. And then we're going to define the other term called alphabets. And sometimes we use the um, what is this called? Sigma, right? It's a Greek letter. Uh, Alphabets are basically set of symbols. So remember, we talked about the set theory. So that means we put different symbols together, and we call it a set. Okay. Now the alphabets we're talking about in the finite automata is always finite. So that means it's a finite set. Now, if we actually use some of the uh, English letters to represent symbols, say A, B, C, D, E, and then we can define an alphabet, which is a set of symbols. So then we can say uh, sigma equals A, B, C, D, E. So that's the alphabet. Okay. So here are some of the examples. Okay. Now, each of these is a symbol. 0, 1, 2, 3. We have 4 different symbols. A, B, C, D. We have 4 different symbols. And we put these together, create a set. That's the alphabets. So that's the terminology we used in the finite automata. We also define a string. Okay. So string is a finite sequence of symbols. Okay, so we put a couple of actually letters together and create a symbols. For example, if we think about like English characters from A to Z, we think about these as symbols, and we define the alphabet, which contains a character A, B, C, D, all the way to Z, and then every English word going to be a string. Okay, so string is a finite sequence of symbols. Okay, from some alphabet. So if we define the alphabet like this, you can use these symbols in the alphabet to define a string, like A, B, C, C, D, A, E. Okay, that's a string. Okay, make sure that each of the symbol is actually defined in the alphabet. Okay, you cannot use like a Z because Z is not included in the alphabet. Okay, so string is generally denoted as W. We use W to denote to represent a string, and the length of a string is denoted as W, and we put the two bars on both sides. Okay, so that basically we use this to represent the the length of the string, which means the number of characters in the string. Now, for example, if we actually use the alphabets 0 and 1, there are two symbols in this alphabet. And then you use the combination of these two symbols, we create a string of 5 digits, 10010. That's a string. So that's a string. And what's the length of the string? It's a 5, right? So that's basically the terminology we will be used in throughout this section. Okay, and let's just continue. Now, suppose sigma is an alphabet, and we put the sigma star. We basically use the sigma star to represent set of all possible strings over the alphabet sigma. Okay, all possible strings over the alphabet sigma. Okay, so if sigma A contains two symbols A and B, and then what is sigma star? Sigma star contains A, B, and all the possible strings. So AA is a possible string, AB is a possible string, BA, BB, AAA, AAB, BAB, and then you can have AAAA. So you can just continue. So that sigma star is actually an infinite set, right? So there's no ending because you can have a string of 100 A and B's. Okay, so 100 symbols. So sigma star, and also we also use another actual notation called a small sigma. Okay, that's we use this to represent the empty string. Okay. Now, why we use a we use sigma to represent empty string? Because empty string means there's nothing in the string. Okay. Um, so in computer language, if we actually define a string, sometimes we're going to say, okay, X is a string. So then you use a double quote and put anything in there. So Bobby or Bob. Okay, so that's a string. So we use a double quote to actually, everything actually characters between the double quotes. That's a string, right? And then we can empty string. That means that there's nothing in there. We just simply put a double quote, and then with nothing in between. That's an empty string. But here we just, the string is defined just like a sequence of characters or a sequence of symbols. That's a string. So empty string, we don't know how to represent empty string. So normally they use a special character uh, to represent the empty string. So that means this is a string, but there's nothing in the no symbols in the string. Okay. So that's the sigma star. which basically contains all the possible strings over the alphabet. So that means there's an infinite number of elements in that set. Now we comes to our important terminology which is called a language. Okay. What is a language? Okay. A language is defined as a set of strings. Okay. A set of strings. This set of strings is actually chosen from sigma star because sigma star is actually contains all the possible strings. So a language basically means it's a subset of sigma star, right? Because language is a set of string and sigma is a set of all strings. So that means a language is a subset of sigma star. So a language is a subset of sigma star. So a language which can be formed over sigma can be finite or infinity. Okay. Now we can define a finite language. For example, let's say we can define sigma as oh, I'm sorry, define a language. So let's say sigma equals A and B. I'm talking about only two symbols. And let's define a language. Okay, define a language, which L. So what's the definition of this language? L is all the strings of length 3. Okay. Now, what is L? That's a definition. All the strings. That's alphabet, A, B. All the strings of length 3. Now, first question, whether is this a finite string or a finite language or infinite language? Finite, right? Okay. I gave you like 2 minutes. Just give me the answer for this. Okay. So, and then I give you another example. Just hold on. So let's see. So this is finite language, right? How many how many how many strings contained in this language?
8.
8. Okay. So all the strings of length 3. Okay. So basically we can even actually list all these strings, right? So because we know that we only have two symbols to build the strings. So we can actually list all the string. So if I actually repeat A 3 times, that's one string, right? Because each A is a symbol defined in this alphabet. Make sure that when you build the language, when you build the strings in the language, the symbols we're going to use should be in the alphabets, okay, in Sigma, okay. So now A looks like that's 1, A, A, B, right? What's next? A, B, A, A, B, B. Okay, let's let's let me erase that one. What's next one? So let's say B, A, A, B, A, B, 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 A, B, B, B. 1, 2, 3, 4, 5, 6, 7, 8. Do I miss any strings in that language? Because it's a string of length 3, so you only actually um, all the strings of length 3. So that's the language I'm going to define. Do I miss anyone? Anything? Any one strings I missed?
No.
Okay, that's all the strings of length 3 from actually from alphabet A and B. Okay, so this is finite language. Okay, I also can actually we also can build an infinite language even with two symbols. We can still build an infinite language, right? One of the example is the Sigma star. Sigma star is a language, right? Because it's basically all the possible strings over the alphabet. So a language is a set of strings. So our Sigma star is the language of set of all strings. So it's a language. Okay. But any other language is a subset of Sigma star. Okay. Let's think about another language, which is infinite language. Okay. Um, okay. Let's say define language L as all the strings that start from symbol A. All the strings that start from symbol A. Okay, so we can actually easily find these strings, but just remember it's difficult to list all the strings start from A. So let me actually that's the next one. Say, okay, so what is the if you can list some of them, right? So the L could be A, just one A. That's a string that starts from A. A B, A A, A A B, A B A, Can I say BA?
No.
No, that's not. So everything actually starts with A. So you can actually just continue with this, creating the list of these strings. So it's infinite. Okay. But it's not all the possible strings, because definitely every string started with B is not part of this language. So it's a subset of sigma star. Okay. So these are actually the we define this as a language. Okay. Now, one of the term is also we call the power of sigma. Okay. We use the notation sigma to the n. We call the power of sigma. Now, it's a set of all strings over sigma of length n. Now, that's kind of interesting. So the first example we talk about when sigma equals a and b, and we talk about all the strings of length 3. So all the sigma with of length 3. This is actually, it's actually a power of sigma, but in this case, we say it's a sigma of all the actual string over the sigma of length 3. So the sigma is AB, length is 3, so it's actually sigma 3, right? Okay. Now sigma 3, or the sigma is A and B, so we can say the set of A and B to the 3. Okay. Now we know that the set of all string over sigma of length 3, if we contains, you know, 2 extra symbols, that's basically 2 to the 3, so which is 8. You have a total of 2 to the 3 elements. But later on, we can figure out the sigma to the n, the power of sigma is actually a finite language. Okay. Even though the n could be a very big one, but it's still finite. Okay. So we already actually listed 2 examples. Now here's another example. Let L be the language which consists of all strings of length 2 generated over alphabet sigma equals AB. So now you have a sigma equals AB, same as the previous example, but consists of all the strings of length 2. Now in this case, the language which consists of all strings of length 2. So that means it's AA, AB, BA, BB. So we only have 4 elements. Okay. So there are 4 strings in this language. Now 4 is actually 2 to the 2 square, 2 to the 2. So that's, oh, okay. So the number of string is 4. Now these are 2 more examples of languages. All string over sigma, which contains AB as a subword. Okay. Do you know how to create that language? Now that's a description, right? The actual language in this case. Okay. So it could be all string over sigma which contains A, B. So let's say AB, right? That's a string which contains AB. AAB, yeah, which contains AB. ABA contains AB. ABAB, we have 2 ABs, but it just say any string which contains AB should be the one. Okay. So we can actually continue to create this one, this language, but this is definitely not finite language, right? So you can create as far as it contains AB, then the rest of string could be anything. We just need to make sure that any string contains A, B as a subword. Okay. Now, what about this? What about this language? All string over sigma 0, 1 that end with 0. Is this a finite or infinite?
Infinite.
Yeah, it's definitely infinite, right? So end with 0. Okay, 0, it ended with 0. 0, 0, ended with 0. 1, 0, ended with 0. 1, 0, 0, 1, 1, 0. Any string that ended with 0, it's part of the language. Okay. Okay, so that's enough of these examples. Okay, let's talk a little bit more about these, some of the propositions. Proposition 1, for alphabet sigma equals A and B. So that means there are two actually symbols in this alphabet with length n. For alphabet sigma with length n, the number of string can be generated is 2 to the n. So we have done this, right? Because we actually see the example like for alphabet sigma equals AB, and with length 2, we generate the four strings. Okay, with length 3, all the actually strings with of length 3, we just list all of them. The number is 8, right? So now the proposition 1 says, if we try to generate all the strings of length n, the number of strings we can generate is 2 to the n. Okay, it's 2 to the n. So if we try to generate a string of length 4, that's 2 to the 4th, 16. You can generate 16 strings. Okay, that's one. Now you can try for length 4. You can try how many. You can list all the possible strings of length 4, and you will find out. You can say A, that's 1. A, B, or whatever, and all B. So you just put all the combination of A and B, and you will find out total number is 16. It's 2 to the 4. Okay. Proposition B. The number of string of length n, possibly over sigma, is the sigma to the n 2 bar. That means the length, the total number of elements in this, or equals sigma to the n. What does that mean? Okay. Now, so that means this condition is generally true, even if the sigma contains more than 2 symbols. Let's say sigma contains A, B, and a C. Okay. So, and then we try to find all string in sigma of with length 4. Or let's say with length 3. Okay. So if sigma equals A, B, and C, so we have 3 extra symbols, and find all the string in sigma with length, let's say length 4. Okay, so we use different number. Now this proposition 2 says the number of string of length 4, possibly over ABC, is, you will get the total number of string of length 4 over sigma is actually 3 to the 4th. 3 is actually the length of sigma, which is 3, right? 4 is the length of the strings. Okay, so 3 to the 4th. So what is 3 to the 4th? 81. Can you believe that? Let's say if I want to actually list all the possible strings, then I'm not going to use length 4, because 81 I have to list all 81 different combinations. Let's say for all strings in sigma with length 2, then that's 3 to the 2s. That's 9, right? It's a 3 square. Now can you list all the strings of length 2 over sigma A, B, and C? Let's say, what are they? I can still create AA, right? Next one, AB, AC. So every actually string start with A of length 2, okay. And then the second one is BA, BB, BC, CA, CB, CC, right? So so 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have a total of 9 different strings of length 2 over the alphabet A, B, and C. Okay. Any questions on this? Okay, let's continue. Okay. So that's all the definitions. That's all the definition of the terminologies. And also we talk about 2 propositions about the number of possible strings with certain fixed length. Okay. Now let's talk about the finite automata. That's the main topics we're going to cover for today. Okay. So the finite automata, FA, or sometimes we call it finite state machine. Okay. It's basically a simple idealized machine used to recognize pattern within input taken from some characteristic set. Okay. So what does that mean? So looks like the finite automata is a machine. So I create a machine. This machine, I can accept a string. Okay, I can accept a string over sigma. Let's say if a sigma is AB equals AB, and then I can create a string A, B, C, or not C, A, B, A, B, for example, that's a string. And I can take this as an input, okay, to the machine. So the machine gonna take the input. Okay. Now, so once I actually put the string as an input to the finite machine, automata, finite state machine, the job of the machine is to accept or reject an import, depend on whether the pattern defined by the finite automata occurs in the import. So that's a finite automata is a machine. So, and I define certain rule for the machine. Say, okay, you are the machine. Okay. And I give you the import. And you check the import and to see whether the import satisfy the rule I set for you. If it satisfies the rule I set for you, then you accept the string. If it does not, you reject the string. Okay, that's the job for the finite automata, for the finite state machine. Okay, now it sounds a little bit confusing, right? But we'll give you an example. Okay, so finite automata is actually an abstract machine, which have 5 elements, or we call the cube. Okay, so the machine going to be defined, when we build a machine, we need some elements, right? The screw, the bolt, some kind of a component. So then we can build a machine. Okay, now the finite machine has 5 elements. So it has a set of states, rules. Okay, the rules for moving from one state to another. Okay, so you can interpret this as a very simple digital computer. Now, what is a computer? The computer basically takes a binary sequence, right? Binary numbers, 0, 1, 1, 0, 0, 1. That's the import for the digital computer. And then you can think about a finite, automata as a digital computer. Just think about this as a computer. And so the computer can take a string. What is that string? That string is over the, binary digitals. So you can think about the alphabet as 0 and 1. So then you can build strings out of these alphabets, right? So these string, so you can think about this string as an import. So you import into the digital computer, which is the finite automata. The finite automata going to process these sequence of digitals, the import, and then you're going to actually either just check the rule, say I accept the import or I reject the import. Okay, it's a very simple computer. It's not really the computer we're using now, but you can think about. But the more complicated machines actually always build upon these simple finite automata. But first we need to understand what is a finite automata, which is very simple computer, digital computer, which accept a binary digitals, a sequence of binary digitals, and then check the pattern of these sequence binary digitals, then decide whether I'm going to accept this sequence or I reject this sequence. Okay, so that's basically defines the finite automata. So the finite automata consists of 5 elements. As I mentioned, it contains 5 elements. Okay. Now, first it contains finite set of states. Okay, finite set of states. Now, what are these states? So I can define the finite set of states as a cube. So I may have 4 states. Okay. Now, these states, in most of the computer, these states could be running, ready, blocked, terminated, or various different states, for a computer system. So I actually use English alphabet to represent different states. Okay, so I can use A to represent a state, capital A. B is another state, C, D. So this finite automata has 4 states, and it could contains more than 4, and it can contains, but it must be a finite set of states. You cannot have an infinite number of states. That's not a finite automata. Okay, and also a sigma, which is a set of import symbols. Okay, sigma could be A and a B, or could be 0 or 1. It's a symbol, right? Just like the terminology we define. So sigma could be A and a B, let's say. Okay, now each finite automata has an initial state. So because the finite automata, in order for the finite automata to run, you're going to start from the initial state. And the initial state is called Q0, is the initial state. So Q0 could be A, could be B, could be C, or could be D, any of the state. So the initial state must be one of the state defined over here. Okay, either A, B, C, or D. Okay, say it could be A. That's an example. Okay. And also, it will define a set of final states. Okay. Final states should also be one of these states. The final state could be C or D. Could. Or could be just C. Or could be just D. Okay. So, but in this particular example, I just say, okay, I define 2 final states, C or D. Now, what is a final state? What is the initial state? What is symbol? So we're going to actually, in the next couple of slides, we're going to explain what is a final state. Okay. And then there's a transition function. Okay. So now you can interpret a finite automata as a state machine, which consists of a couple of states, 4 states, A, B, C, and D. Okay. So there are 4 states. And then the transition function basically says, okay, the state can be started from A. So I can say A is initial state. Okay. So initial state is A. And I can start from A and transit to B, from A to B under certain condition. Okay. What are these conditions? We will talk about this later. And then the state B can be switched to state C under certain condition. Or B could be switched to another state D under another condition. Under certain condition, you're going to switch to C, under certain condition, switch to D. Okay. And even also from A, under certain condition, you can transit to B, and under certain condition, transit to C, up to D. Okay. So we basically define a couple of states and define the rule. That's a rule in terms of how we're going to transit from A to B, how we're going to transit from B to C. And that's a rule we're going to define. The rule actually defines the states, and the rule defines the finite automata. Okay. Now let's give you a little bit more terminologies. So in one of the terminologies called import for the finite automata, import is a string. Okay. So import is a string fed to the machine. So just like I said here. Import is a string. That's an import. Eventually going to send it to the string, or send to the finite automata, to the machine. And which the machine will determine whether it is a part of the language that the machine was designed for. Okay. So here's the deal. So I create the finite automata, the finite machine. The machine gonna take a string. Okay. Now if the string satisfies certain pattern, or we can say if the string is part of the language we define, then the machine gonna accept it. If the string is not in the language, we reject it. Okay. So it's part of the language that the machine was designed for. So the string must only be made up of the symbols from the machine's alphabet, sigma. Okay. It does not make sense to feed the 3 to the machine that only reads 0 and 1. So that's basically means the string, once we actually feed the string must be, the symbols in the string must be actually in the alphabets. Okay. So that's the import. And the return, we define the return. The returns of running the machine on the given import. So that's the results of the running the machine on the given import. So once actually I send the import to the machine, the machine should return something, right? Okay. So the return, basically, the final return going to be either accepted or rejected. So there's only 2 results for the return: accepted or rejected. Okay. So basically, in this indicating that whether the import string is respectively part of the language or not. If the if the import string is part of the language we defined for the machine, then we accept it. If the string we actually import string is not a part of the language defined for this machine, then we reject it. Okay. I'll give you an example. Don't worry about this. So later we will introduce a machine capable of generating an output string to return in addition to its standard return value. Okay. So, but initially we're going to say only accept or reject. Now the state basically is a resting place while the machine reads more imports if more imports is available. So the it's a rest. The start state is the initial state. That's Q to 0. Okay, that's a start state to 0. Now the final state. Remember the final state here. Set of final states. Okay, what is final states? A final state is also called accepting state. A set of states which the machine may halt in, provided it has no import left in order to accept the string as part of a language. Okay, so if I have an import string, and for each of the symbols in the string, I decide which state I'm going to go. And the next import, I decide which state I'm going to go. And eventually, if the string contains, import string contains only 5 symbols, then it can actually move from one state to the other state 5 times. And eventually, it can actually rest in one of the state. If that state happens to be the final state, that means this string is accepted. Okay. And also called the rejecting state. So if the string actually end up in a rejecting state, then that string going to be rejected. Okay. In certain situation, so you will actually, the finite automata, we will enter into a state called dead state. So dead state means no matter how many input we're going to actually continue to feed. So there's no way we're going to actually end up with accepting state. Okay. So, and then a transition. Transition is a way for a machine to go from one state to another, given the symbol from the input. So we're going to transit from one state to the other under circumstances. What is this circumstance? That's the symbol. You know, if which symbol will lead A to B, which symbol will lead A to D. Okay. So now we have enough of these definition. Let's actually move to the real things. We can actually start with an example. Now, once I start the example, I will be back to the definition so you can actually understand what does this definition means. Okay. Now, so once we talk about a finite automata, and there are two actually types of finite automata. One is called deterministic finite automata, which is also use DFA. Okay, deterministic finite automata. Non-deterministic finite automata is all called NFA. Okay, we can talk about both, but initially we're going to actually talk about a finite, deterministic finite automata, DFA. Okay. So for DFA, it contains 5 elements. Just like any finite automata, it contains 5 elements. Okay, so Q is the finite set of n states. Okay, this is just the same as a general finite automata, and also true for the deterministic. And sigma is the alphabets of input symbols and the machine will use. Okay, same thing. Q is a special start state. Okay, Q should be also in Q0 should be also in the Q, which is the set of the end state. F is a set of the accepting state or final state. F is also a subset of Q. Okay. Now sigma is the transition. Okay. So it's called a transition function. Now, what is a transition function? Transition function gonna actually, you're gonna move from one state to the other state and depend on what is the value of the symbol. Okay, so the sigma is a function which has 2 parameters, and then the result going to be another state. So the sigma is so the transition is determined like for example, the current state is A. Now, what is the next state? It depends on what is the input value. Okay, if the input value is A, then we're going to go to B. If the input is B, and we're going to go to C, another state. Okay, that's an example. Okay, let's take a look at the example here. Okay, let's say we want to define a finite automata. Okay, so the finite automata use 4 symbols. So that's the alphabet. Epsilon contains 4 symbols. So, and the length of string. So that's something we already talked about, right? We know all this. Okay. Now, in order to actually do this, we actually first need to build the DFA. And then once we build the DFA, then we can actually send the input and check each of the string, whether this string actually satisfy the DFA rule. Okay. Now, how are we going to build the DFA? So we're going to actually use the graphics to build the DFA. And we use a circle to represent a state. The circle with a name inside represent a state. Okay. So the name could be a name, right? Or could be in our example, mostly we just use the capital English, English letter, capital letters. Okay. Now the arcs, it's actually the line with arrow labeled with an import alphabet defines the transition. Okay, defines the delta, the transition. Okay, so the initial state is denoted by an empty single incoming arc. Okay, and the final state is indicated by a double circle. So now let's build a finite automata. The circle with the name inside represents a state. So now suppose we have a 4 state. Okay. The first state I use the name A. The second state I use name B, C, and D. Okay. Now the arc. So then I just go from here A to B. And then let's say the sigma is A and B. I build a finite automata over the sigma, the alphabet A and B. Now, so the arc labeled with the import alphabet show the transition. So I'm going to say, if the import is A, the state will transit from A to B. If the import is B, it will transit to C. Okay. And then I'm going to define, if the current state is B, then I'm going to say, if the import is A, I'm going to transit to C. If the import is B, I'm going to transit back to A. Okay. If the current state is C, okay, then if the import is A, I'm going to transit to A, transit to D. If the import is B, let's see. For B, if the transit B, back to A. If A, it's go to C. If B is back to A. Okay. Now, if the import is B, it's also go to D. So anyway, so now this is a very simple finite automata, a simple finite state machine. And I also say D is the final state or the accepting state. Now, how does the finite automata works? So let's say if I give you an import string, say A, B, B, A, A. Okay, that's an import string, right? Okay, A is the initial state. So for the initial state, I use the empty single incoming arc. So it's an incoming arc with empty. There's actually nothing. So it does if the arrow from nowhere, okay, that means this is actually initial state. So the state, okay, so that's single, not the double. Okay. Now how can I check? And then that's the finite automata. Okay, that's a deterministic finite automata I just created. That's a machine. It's a finite state machine. Now, how does this finite state machine works? Okay, then I give you a string built from A and B, right? A, B, 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 A. Okay. Now I check the string and I check the first symbol, which is A. Okay. So now what's the situation? The finite state machine actually finite state machine or finite automata start from A, right? So the initial state is A, and the initial symbol is A. Now with A and A, what is next state I'm gonna go? Now it's defined. This is a rule defined in the finite automata. So the initial state A, the import is A. So then I'm going to B. Okay, that's a transaction. So these finite automata that defines the transaction, the last transaction rule. Okay. It defines the transaction rule. So you have the initial state and also the import. And then it can decide what is the next state. Okay. So the initial state is A. The first import is A. So A and A goes to B. Now, so we're going to the second one. Now the state is B now in the finite state machine. The import is B. So then what's the next state? So if I draw this diagram, I can say, okay, the initial state is A. So because the first import is A, so then I'm going to B. Now, what is the next state? Then I check the import value. The first value is A, the second value is B. So if I have a B and the second value is B. So where am I going to go? What's its next state? What is next state based on the finite state machine?
B.
Back to A.
Back to A. Because the current state is B and the import value is B. So I'm going to follow this arc back to A. And then the next value is B. And the current state is A now, right? The current state is A. And the next value is B. So A value is B goes to C, right? So now the current state is C. The next import value is A. Let's actually go up. So I'm running out of space on the right. So I'm going up. So the import is A. So the import A, B, B, A, A. So I'm going to follow A, B, B, A. So C, the import is A. We're going to go to D, right? And then, well, what's the next state we're going to go? It's A. It does not define. So this finite state, that's the deterministic finite automata is not complete. So I need to continue to build this. Now let's say, if the current state is D, I'm going to say, if the import is A, I'm actually point to itself. So that means if the current state is D and the import value is A, I'm actually pointing to itself. So now, if that's the case, now if it's B, if the import is B, the current state is D, and the import is B, I'm going back to B. Now with this case, so the current state is D, and the import is A. What is the next state?
D.
Still D, right? And then there's no more import. So that's the final state. Now, because D has a double circle, so that means it's a final state. Double circle means it's an accepting state, right? So then there's the finite state machine. That's the finite automata we defined here. Accept this string or not. So that machine gonna accept that string, right? Because A, B, C, D start from A. Eventually, we actually move to D at the very end. So which is accepting or final state. So we're gonna, this machine gonna accept this string. Okay. Now what about A, B, B, A, B? So it's still A, B, B, A, and the final one is B. If final one's B and here's a D, if it's B, you're gonna go back to B, right? If it's B, you're gonna go back to B. Do you think this finite automata gonna accept this string? Do you think that import will be accepted or not?
No.
No, because we run out of the import, but we end up at the B, and the B is not the accepting state. So that string will not be accepted by these finite automata. So that's basically, so we actually draw this diagram to define the finite automata, or sometimes we first give you the rule. So what this machine can accept. So we draw this finite automata, and then we check each of the import value to see whether this finite automata can accept this import or reject the import. So we can actually work on a simple machine, but once the machine gets more and more complicated, then we can actually interpret this as like a computer. A computer is a very complicated finite automata. It can accept a very complicated string by its complicated rule, right? But here, it's very simple. But the complicated one always start from the simple one. Okay. I'm gonna skip the non-deterministic finite automata for now. Okay. I will be back once I finish the finite deterministic finite automata, DFA. So we're gonna go back to the NFA, which is non-deterministic finite automata. Okay. Now let's start with example. Okay. So let's build a DFA, the deterministic finite automata, that accepts string that contain 0, 1 as a subword. Okay, so in this case, sorry. I just accidentally hit a key, so it just quit. So, so let's say we build a finite deterministic finite automata that will accept strings that contains 0, 1 as a subword. Okay, now first thing, let's build this the finite automata machine first. Okay. How many states we're going to end up with? I don't know. Let's see. But we first just focus on how to build this DFA, which accepts strings that contains 0 as subword. Okay. So I can start with the initial state A. Okay. Now, we want to accept strings that contains 0 and 1. So the sigma is actually 0 and 1, or two symbols. So that's the finite automata we're going to build now. So if I don't say anything, by default, we always assume sigma is 0 and 1, because mostly when we build a finite automata, we always assume that it's kind of like a simple digital computer. So the digital computer only accepts the input of 0 and 1. Okay, so that's why we always think about the language contains 0 and 1. Let's say, suppose if the input is 1, or input is 1, if the input is 1 in the first character is 1, what do you think? We're going to go to another state, right? Now, the goal, what's the goal? When we build this finite machine, what's the goal we have? We want to make sure, so if the sequence contains 0, 1 as a subword, so for example, like a 0, 1, 0, 0, 1, 1, 0, 1, these are all accepting string, right? Because it contains 0 and 1, 0 and 1. But this is not. 1, 0 is not. 1, 1, 1, 1, 0 is not, because it does not contain a subword 0, 1. But 1, 1, 0, 1, that's it. That's accepted, right? Should be accepted. So as far as the string contains 0, 1 in the string, then that string should be accepted. So if the first actually input is 1, then we're going to say we go to the B. Of course, do you think B is going to be the accepting state? Of course not. If it's 1, then definitely 1 is not accepting string, right? Now, what about the 0? So if the input is 0, that's a good sign. Looks like a 0 is one of the actually the first digital in this subword. So then we're gonna actually say I'm gonna create another state C. So when the input is the initial state is A, when the first input is 0, I'm gonna go to C. The input value is 1, I'm gonna go to B. B and C are two different states. Okay. Now suppose the current state is C. So that means the 0 is actually was imported before. And then the current state is C, and the next import is 1. Then we go to another state, D. What do you think about D? So the string sequence of strings is 0, 1. So it's actually 0, 1. So what do you think about D? D should be
Accept state.
it's accepting state, right?
Yeah.
Now, once we are in the state D, and if I import another value, 1, actually, once we are in the D, it really doesn't matter. So if it's next to 1 is 0, 1, we continue actually back to D, because if we actually the first symbol is 0, second symbol is 1, first symbol is 0, second symbol is 1. Now it really doesn't matter whether the third value, right? If the third value is 1, this is still accepted, right? Because it still contains the subword 101. So it doesn't matter what's the follow-up symbol. This string was always accepted, right? Does it make sense?
Yes.
So if it's 1, we were still back to accepting state. If it's 0, we also back to accepting state, because 0, 1, this subword is already generated. However, so that's one probability. Now let's go back to A. Now if A is 0, then we go to C, and if after C, if the import is 1, then we're done. So if any import string which follows that path, that's good. We accept them. However, in another path, if the initial value is 1, we'll go to B. That sounds bad, right? If the next import is 1 again, what do you think? 1, 1. That's not good, right?
Nope.
Or let's say, just forget about this. If the next import is 0, we just let it, we're going to go to C, right? We're going to go to C. Is it right? Because that means if the first is 1, second one is 0, and then we go to C. If the third one is 1, good. We got the string 1, 0, right? So now it doesn't matter what's the follow-up. This is going to be accepted, right? So if it's 0, we go to C. Hopefully the next one is 1, then we accept it. So that means 1, 0, 1 will be accepted. Now, what about 1, 0, 0? Next one is 0. Or 0, 0. What shall we go?
Stay in the same place. C.
I think the best way is to stay in the same place. If the import is 0, we stay in C. Okay. Because like a 0, 0, if you have a 0, 0, 0, 0, it's okay. There's still hope, right? Once we find a 1 here, then this string going to be accepted, because it doesn't matter what's the follow-up, because you already find this one. So it doesn't matter how many zeros we actually experience. As far as it's 0, it stays in C. But once we got a 1, then you go to the next one. Go to D. Now, what about a B here? If the B is 0, we go to C. But if B is 1, next import is 1. We stay in B, right?
Yeah.
We stay in B. So that means if we have a 1, 1, 1, 1, 1, and so you're gonna keep like a initial state is A. If the import is 1, then we go to B, and it's 1 again, we stay in the B. 1 again, we stay in the B. 1 again, we stay in the B, and until we find a 0, then we go to next to the C. C is actually just one step closer to D. Okay. So hopefully that's the one. That's the finite automata we are going to build. Now, the next thing we're going to do is we're going to check whether this is going to work or not. Okay. So let's actually put the 0 here. That's 0. So in this case, so the diagram is like this. Okay. Now we're going to check. So let me actually make it clean. I'm going to clean up everything here. Okay. So that's the answer we have. So based on this finite automata, so we start from A. Okay, that's a start state. Okay, now if the import value is 0 and the current state is A, import value is 0. Import state is A, import value is 0 based on this finite automata. So what is the next state? It's C, right? Initial state is A, import is value is 0, we go to C. Now, if the import value is 1, where are we going to go?
B.
B. Okay. So then, from that's the transaction function. So if the current state is A, now if the import is 0, we go to C. Import, if the import is 1, we're going to go to B. Now, if the current state is B, let's see where we're going to go. So if the import is 0, we go to C. Import is 1, we stays in B, right? So import is 0, we go to C. And import 1, we stays in B. Okay. Now what about a C? For import is 0, we stays in C. Import 1, we go to D. Import 1, we go to D. Import is 0, we stays in C, right? Now what about D? Import is 0, we stay in D. Import 1, we stays in D. So it's D. D. So that's the final state or accepting state. Okay. So we have 4 states, A, B, C, D. Okay. So alphabet is 0 and 1. And the start state is A. And the final state is D. I put the asterisk here or star here. Now, once we actually build the finite automata based on this rule, that's a rule. Okay. Now we can check each of the import string. Okay. Now let's actually take a look at the example. Now, actually, when we check this string, we know this will be accepted because it's a 0, 1, a 0, 0, 1. So we have a 0, 1, right? And this is 1, 1, 0. So there's no 0, 1. So this will be rejected. And this is, what about this? That contains
Accepted.
Accepted, yeah. Rejected, right? Now let's check with the finite state machine, because we know these two will be accepted and the middle one will be rejected because we are human being. We can simply look at the string. But think about, it's not you going to determine, it's the machine that will be determining whether we're going to accept or not. So think about this. We can always look at the string and say, oh, that's simple. This is what be accepted. This will be rejected. The machine, now we're going to build a machine to do the job, not you. Okay. So if it's a machine, then based on the transition function, what is the transition function going to go? Let's say the initial state is A, right? So the first input is 0. First input is 0. So we have a look at the transition function. So it's A, initial state is A. First in transition is 0. So what's the next transition? The next state is C, right? Okay. So then what is the next input? It's also 0. Okay. So we're in the state C, and also the input is 0, C and 0. So we stay in C, right? Now the third one is 1. The current state is C, and the input is 1. So now we end up at the D. Okay. And we're not done yet. We have 2 more input value. So next input value is 1. Okay. The fourth input value is 1. And the D, 1 stays in D. And then the next input is 0. D, 0 stays in 0. So it's, which is accepting state. So we accept it, right? Now let's build another path. Start from A for this string. It's 1, A, 1. So it's A, 1. So we're going to end up in B, right? Now we are in B, B and a 1, because the next input is 1. B, 1. B and a 1 stays in B. And the next is 0, right? 1, 1, 0. Okay, B and a 0, we're in the C. And there's no more input value. And the C is not accepting state. So we reject it. Okay. So 1, 0, B, 0, B, 0, C. And a C, 1. C, 1, D. Accepted. So you can actually use the finite state machine, and then we can actually, for each import string, we actually just make sure the final state. If the final state is accepting state, then the state machine, the finite automata, are going to accept the string. If the final state is not accepting state, like a C, we reject it. Okay. Any questions on this? Let's move forward. Okay. I think I'm going to give you about about 4 minutes. Hopefully, you can actually work on your own. And also, in the meantime, I'm going to stop the recording. I'm going to separate the recording into 2 parts, because Google doesn't like a very big